All right, welcome back to System Software. We are right at the beginning of learning about processes. And today we're going to continue with some of the fundamentals of processes, how you can manage these with your shell, which will help illustrate how these actually work under the hood a little bit. And then we'll go into actually doing systems programming, creating new processes, running programs, manipulating their I/O, and then eventually we'll actually write a shell interpreter ourselves. Something along the lines similar to Bash. All right, before I get started, questions about last time, questions about homework, questions about project. What questions do you have? All right, let's go over the homework. So number one, what's a process? A running program. Yeah, that's the definition of a process. And what's the difference between a running program and a program? Or what's a program? It's a set of instructions that can be anywhere. They can be stored on the machine, in your mind, on paper. What's that? I mean, in some sense, it's a procedure. It's an algorithm. It's not really well, it might be mechanically realizable. I don't know. It depends on how specific it is. It's not computing. It's not computing a number. Okay, that's a good point. Yeah, a set of instructions that performs a computation, maybe. Then you have to define computable, what that means. And this gets down. Take a theory of computation class, and they'll go into like Turing and Church and Gödel and all the models of computation, the hypotheses or the theses about what computation is. But for our purposes, I'm assuming we mean machine instructions. And then a process is a running program, a program that is currently running. All right, good. What about standard I/O? What's standard I/O in the Unix world? What's that? Well, yeah. So yeah, I mean that's true. I/O, the kind of Unix model of I/O is all just files. They use files to model I/O. What is standard I/O for a process? Yeah.
It allows you to use input and output from outside the program instead of having a hard code in every single possible.
Yeah, that's why it's useful. So you can the process that's creating your process, that's starting your running program, can define what the input and output of your process is. And all you have to do is you just have to read and write from the standard I/O files. And what are those? In C, what are they called in C? Yeah, STDIN, STDOUT, STDIR, standard in, standard out, standard error. All right, good. So that's standard error or standard I/O. And that's why you can just write printf in your C code, and you don't have to tell it where to write this. It'll just write it to wherever the Bash process has set the standard I/O to be. All right. So how do we, if we run the ls command, how can we save its output to a file, knowing what we know about standard I/O and hopefully remembering class? How can we do that? Yeah. ls, and then a little arrow. So let's go to the header directory. So ls lists the directory, and then this little right angle bracket or right arrow, kind of looks like an arrow, allows us to save a file. So what did I call it? Results.txt. Now I'm not saving it to the user include directory because I don't have permission to do that. So I'm going to save it to my home folder. And you can see if I look at this file, results.txt, it contains the output of ls. Yeah?
Did you want both just putting it out to a file and then also having it to where it doesn't overwrite as well, or did you just want one or the other?
This will overwrite.
Okay.
The arrow will overwrite.
Because I know if you do the double arrow, it doesn't overwrite, it just appends it.
Oh yeah, that's right. So double arrow, as I very quickly went over last time, double arrow will append. So if this... No, it doesn't matter. So if you try to append to a file that doesn't exist, it'll create one for you, probably using the create flag, and it probably just does create truncate. But yeah, if you do append, it will just create a new file. So new results.txt. This file doesn't exist. I'm hitting tab. It doesn't exist. And now new results will have the content. I could add to it with append like this, add a bunch of other directories, and you'll see inside of new results, it has the old results, and also you just have to believe me that this is the stuff. This is the stuff in user. Let me do a different command here. So this is appended. I used echo. This is appended. So knowing what you know about standard I/O, what does the echo program do? How much you write it and say, what to do? Okay, it outputs a standard out. What does it output to standard out? The argument. This is the argument to the program. So echo it's a program written in C, I think, that somebody wrote. So what would that code look like, knowing what you know a little bit about file system calls and I/O? What might that program look like? Let's write some pseudocode for echo. So here's our int program. How might we write the program echo? Yeah.
Did you say that like standard in, standard out, and standard error, like a file descriptor?
That's right. Yeah, that's right. So there are file descriptors. They're really file descriptors are integers, and the kernel manages your open files for your process for you. And standard in is 0, file descriptor 0, the first one, base 0 indexing. Standard out is 1, standard error is 2. Let's see if this is documented here. I don't know if it tells you here, but that's what the Unix standard will use. How do we write to standard out? How can we print a string to standard out? Printf, yeah. So printf by default prints to standard out. Did you all learn? Did you learn fprintf? Who learned about fprintf? Yeah, it prints to a file, right? So we could also, where's my code? We could also write this, fprintf standard out, and then some output. So these two are equivalent. This is the same printf. You could define a new function, printf, that just calls fprintf standard out. Okay, so that's how we print to standard out. Now how do we print the arguments to standard out? Yeah, you could just grab the first argument. Echo, it really prints all the arguments, but we can make a simplified version and just do something like this. And this would be basically, well, probably a safer way to do it is like this. And here's our echo program. Actually, let me just save it. Let's actually run it. Here's my echo program. Let's see if we can actually get this to work. All right, so how do I run this program now? Do I just type echo? Which echo is run if I type, what's that? // echo. And so to prove that this is my echo, I'll change the string. Let's see if this works. There we go. There's echo. Echo is a very simple program. And it's made simple because the system manages arguments for you, it manages I/O for you, and then you as the programmer don't have to worry about I/O at all. You just write your code, write your algorithm, and it will just work. All right, questions on this? Questions on the homework? Standard I/O? Yeah. Those keywords are defined somewhere in the header, but these keywords just map to. I think they just map to numbers. So if I were to do this, I think I can think I can show you what this looks like. Okay, so they're variables. They're variables defined somewhere in standard I/O. I have no idea where they're defined. They're probably defined in here somewhere. Okay, so they're declared here as files, and the kernel when it the kernel will the bash will work with the kernel to open these files and make these file descriptors available to you. And we'll actually see how to set that up when we write a shell. We'll write a shell that will actually open the files for you, and for the child process that we create. But I forgot. They're not file descriptors. These are C library files. Underneath of them will be the file descriptors, the kernel file descriptors. All right, other questions? Other questions on this? Yeah.
So just to confirm, writing fprint of std out and your string is the same as just print up with that string.
Yep, that's right. Yeah. And I wonder if we can actually see the code for printf somewhere. Okay, so they actually implemented it. We don't have the implementation here. We'd have to open up the standard I/O library to actually see the implementation. But yeah, it's equivalent. The documentation, I think, should tell you this. So you can see here, this is section 1. There's a bash command called printf, but we want so yeah, which man section is this printf going to be in? Is it a system call or is it a C library call? C library call, which is section 3. So let's see if it tells us what printf does. Functions printf, vprintf, write output to standard out. All right, other questions on kind of basics of processes, standard I/O? Yeah.
This might be a little off topic, but in the manual they mentioned like 5 different types of printfs.
Yeah, there's lots of types of printfs. Let's see. So some of these, the sprintf ones, those are for writing to a string instead of to a file. The N ones will restrict how many bytes are written to it. That's so you don't have like buffer overflows. And I don't know what the V ones do. What do the V's do? I don't know what the V ones do. Loads data from locations defined by a V list. Okay, so they have a different signature. They take a list. Oh, this is for variable arguments. Don't worry about that. There's a feature of GCC that allows variable argument length functions. So I guess they have a way to print those out. Anyway, yeah. All right, other questions? Other questions on this? Questions on the FS homework? Who started it? Who started the project, rather? Okay. So we have a little time. Let's see. 2 weeks left. So you've burned through a third of your time. All right, so if there's no other questions, let's continue with processes. So just a quick reminder. Oh, yeah, sorry, go ahead. Oh, yeah.
Is the bonus just for ourselves to practice, or is it extra credit?
No, you can get extra credit for it. But the bonus project is not kind of systematized. So if you read the description, just propose something to me, either on EdStam or office hours, and then before the end of the semester, demonstrate in person your code. Walk through your code and show me it running, have test cases, and this is my sort of fluffy, less well-defined part of the grade. So otherwise it would just be part of the class, right? So there should be like sort of above and beyond the code you do in the class, and like unique. It's something that you investigate for yourself. So just like demonstrate that you understand what you did, you had some interesting problem, and that you wrote code to do it. So I give some suggestions for things that could form part of a bonus project in here. So I mentioned, I have bonus project ideas. So you don't have to use those. You can come up with something on your own. So for instance, one student last semester did like network sockets, which are they're not using files strictly, but it's using the read and write calls as part of the network stack, they behave similarly once you open the network socket. All right, other questions on the FS project? Yeah. Yeah, thank you. Yes, I'm recording. Thank you. All right, so processes are running programs. And last time we just talked about I/O. Just in case you don't remember, you run programs in Bash by just typing the name of the executable. And where we left off was with redirection. So once you have a sense of standard I/O, then it makes sense to have, in Bash, it makes sense to have a way to redirect where the I/O goes. So by default, when a new process is created, when Bash creates a new process for the ls program, new processes by default will just inherit the creating process, the parent process's I/O. So right now, Bash, if I type, its output is the terminal and its input is the terminal. That's why my key commands are making its way to the Bash program on Eustace, or actually on my machine here on Eustace. But I can redirect where that input and output comes from through these commands. That's why when I do this redirection, the ls output, you just don't see it to your terminal because it's no longer being printed to your terminal. The Bash process will create the ls, process for ls, and then change which open files it has for standard I/O. And same thing with reading. So if I type cat and just hit enter, it's waiting for input on standard in, which right now is the terminal. So it's waiting for me to type input on the terminal. But I could redirect that input using the left arrow, say from another file, and now cat will use that file as its input. Yeah?
Can the output, or can outputs from a program be taken as inputs, or as arguments from a program?
That's a very good question. That's exactly the next section of the talk, which is called piping. So that's very smart. So this is exactly what this was the style that the Unix creators had in mind with this redirection. They said, well, all right, not only is the I/O independent of the program, we can actually compose larger tools by just combining lots of little programs together. And the way we do that is to use the standard I/O. We can chain together an arbitrary sequence of programs without having to create any intermediate files. They'll just flow through a pipeline, the inputs to the outputs between programs. And so that's actually the next section of this talk. But before I move on, questions about redirection. So it makes sense when you understand standard I/O. And then once you have this is a really powerful command line feature. Because if you're doing testing or working with text, you're writing scripts, you're doing sysadmin, it's really, really useful to be able to it's like doing plumbing. You can redirect where these flows of information and text go without having to do any reprogramming of the code. All right, any questions on redirection or standard I/O? Yeah. No, it's literally the number 2. So you could also write 0 and 1 next to these. So this is the file descriptor number. And so in the kernel, the first 3 file descriptors, 0, 1, and 2, correspond to in, out, and error. So this is really just saying write the file descriptor 2 from whatever program you're running. So for instance, let's run find here. So I'm going to get some, even though you can't see it, it's going really fast. I'm going to get some errors here. So I can redirect file descriptor 1, which is standard out, to find.out, and I can redirect standard error file descriptor 2, which is standard error, to find.error. Now notice also I can use multiple or all of the redirections with the same command. So here, what's find.out going to contain? So find lists all the directories, including its subdirectories. So this is going to contain the list of all the directories and subdirectories from root. And this is going to contain any errors that the find program emitted. So notice I'm not going to see any output here. It's just waiting for the program to finish. So if I kill it, I can look at find.out, and it indeed contains this giant list of all directories on the file system. But some of those are not accessible to me. So find.error contains all the stuff that find wrote to standard error, which was, in this case, permission denied errors. So these are not part of the, this is, you can see an example of separating the output of your program from error messages or log messages. All right, questions? Questions on this? Okay, so let's go into piping. So there's some examples in here. You can look for yourself. All right, so the really cool part about this standard I/O is creating pipelines. So as I said before, we can create complex tools from simple existing programs. So if you were thinking, well, okay, I need to write a program that's going to search for, say, C header files. You don't have to write a program to do that. Instead we can do something like we can take an existing program like find, which lists all the directories, and that alone kind of seems like, well, that's kind of a silly program, right? It doesn't really do anything. But when combined with other tools like grep is a tool that will match lines of text. So if I say grep hello, it's going to take standard in, and whenever I match a line of text that has hello on it, it's going to output that line to standard out. So it's like a filter. It's a filter for text. And it alone also seems like, well, okay, that's a very simple program. But if I combine this with, say, find, I can ask it to search for files that end with .h. So don't worry too much about the syntax of grep. It's a little esoteric, but this is finding files that end with .h. And so now when I run this, oops, I piped to it. So I'm getting all files in, well, let's just do user. Getting all files in user and piping that output to grep, because remember, find just writes standard out, and grep reads from standard in. So this pipe says take the left program standard out and redirect it, replumb it to the standard in of the right program. So what do you think's what am I gonna see when I write this out? This is what I saw when I ran find by itself. What am I gonna see here? Header files, yeah. So it's going by really fast, but you can see, and now grep has a mode to colorize the output. You can see the only things I'm getting are lines that match ending with .h. So if I had run this without piping, you'll see I get lots, all the files. So this is files that don't end with .h. So these end with .hi, but that's not ending strictly with .h. So other files are being. So you see how that works? So and this comes down to the Unix philosophy, which was articulated by this guy Don McElroy, who I think implemented a bunch of this stuff and outlined this philosophy in this very old 1978 at this point, this introduction to this book, which it's on archive.org. I don't know. It might be copyrighted. I don't know. But it's on archive.org. And he articulates this in this book, which is a guide to Unix. Or actually, it's the forward to the guide. Actually, this is only the forward. You'd have to track down the whole book. But anyway, this is the philosophy. Make each program do one thing well. So rather than trying to build a new custom program every time you need to solve a new application, make a bunch of kind of Lego bricks, like a bunch of very specific special purpose tools that do one specific task really well and avoid bloat. Avoid taking an old tool and be like, well, I have a tool that prints all the files, so let me add a feature to filter out files. Actually, Find does have a feature to do that, so he might have thought that was bloat. And this is the standard I/O part. Expect the output of every program to become the input of another, even if you don't know what that program might be. And standard I/O is what makes this possible, because when you write your program, you just say, all right, well, all my output's going to go to standard out. And this even implies that the output should be kind of machine readable or readable by another program, not just kind of arbitrary text, but something well-defined that can be processed as input. So let me show you one more example. I have a tool called sort, or Unix has a tool called sort. And what do you think it does? Well, it takes a list of lines in the input, and it sorts them. So it's a little hard to see where the output is because it's all going to the same terminal window. But here's the sorted output of the lines. So I could say ask find to give me all the directories, ask grep to give me the header files, and then ask sort to sort them. Because this is going to be a lot, I'm going to use another tool called head, which I can tell it to only give me the first 40 or any number of lines. So what this pipeline is saying is give me all directories and user, give me filter out only the directories that end, or only the files that end with .h, give me the first 40 of these, and then sort them. So here is the list, the first 40 files from user that are .h files that end with .h, and sort them. So here's the sorted list. And so each of these tools is a well-defined tool that does one task really well. Sort doesn't have to know about how to search through file systems. grep doesn't have to worry about cutting out the number of lines or finding files or doing sorting. We can build up larger applications through small tools. And the great part about this is we don't actually have to go into C and actually program anything. We can do this entirely from the bash interface. And this is one of the reasons that the command line, particularly Unix command line, is so powerful, because you can build very sophisticated, complicated programs and systems strictly with the command line in many, many cases. You can even do network programming here. So I could then, using a tool called netcat, which is like cat just takes standard in and prints it to standard out. Well, netcat takes standard in and prints it to, or writes it to, a network socket. So if I had on another machine, I can open a server that will listen, and I could write this information out to a different machine using netcat. So I could say, I don't know if Eustace would want me to pass stuff to, well, actually I probably could open a port, but I won't do this now. But you could say pass this to Eustace at some port on Eustace. Actually, I'm already on Eustace, so it doesn't matter. So I can develop sophisticated programs, including like network programming, all sorts of complicated text processing, just by using this Unix style of process management, basically. Okay, so that's the second principle. And then there's other sort of principles about system buildings, like, this is kind of what would be called to maybe agile today, like test things early, do the minimum viable product. These are the sort of modern buzzwords for these. So this is kind of an old one. So basically automate what people would do is basically what it's saying. So this I think everyone sort of has internalized this already. All right, questions about this? Questions about this philosophy? Yeah.
What is this sort based on? Is it numerically?
Oh, that's a good question. So this is a place where sort does have features to allow you to specify what sort means. So by default, it's doing, I think it's just doing like ASCII sort, like ASCII character sort. It has a default sort mode. I don't remember which one it is, but I think it's probably just doing like looking at the ASCII codes and sorting those from the beginning of the file. But you can, for instance, so one thing I use a lot is this human numeric sort. This is kind of a useful one. So if I want to say, so there's a tool called DU, which is disk usage. And this, I can use this to, so some people had issues with disk quota, running out of disk quota on Eustace. So you can use DU to, so I have some of these like hard-coded in my muscle memory, but I can use this to give me all the sizes of files in my directory. So don't worry too much about the commands here. This is just saying, give me human readable outputs like 386M instead of its default, which is I think blocks. Give me a summary, which is what C means, that's the total, and then only look one directory deep. So don't worry too much about this command, but know that this will give me the file sizes and directory and some directory sizes of each file in my current directory. And now they're all kind of a mess, right? They're all kind of in some random order. I can use the sort. So if I use sort here, it's going to sort it by numerically, right? This doesn't really make much sense because I have 9 megs coming before 900K. So sort you can tell sort to sort instead by this format. So sort.h will sort by this format, and voila, now I have the actual largest stuff at the end. So I use this frequently actually for like, you might use this in a file explorer, for instance, but some things I can do faster this way. I can easily find this more quickly. Also note that in your Windows file explorer, actually I don't know if they do this now, but directories will just be the directory size. So this boost directory, because remember the directory itself is just a mapping from names to inode numbers. So this directory itself, the directory itself is actually really small. It's just 12K. But the contents of the directory is 162 megs. So that's because all of the files in the directory, if you sum them up, you get 162 megs. But remember, the directory itself is literally just a map from strings to inode numbers. So that's its actual file size on disk. The DU tool will sum those up, and I can use DU to help me just do like space management. Does like Windows File Explorer do this for you? I think macOS Finder, there's a flag to turn this on. Does Windows do this? Where it shows you the contents? You can turn it on. I can right click and it'll tell, okay. So I can do this with one command. You'll have to like click around a lot to do it on Windows, I guess. Yeah.
But if you right click properties, and it's a big folder, I think it has to count every single file.
Oh yeah, it will. I mean, this does too. Yeah, that's how you have to, I mean, because of the way directory files work, that's what you have to do. You could cache them. I think macOS will cache those results. There's a flag you can turn on and it'll sum it up in the background and then like save that sum for you, so it doesn't have to keep recomputing it. But anyway, just some kind of like little tricks that I use frequently on the command line. Yeah.
Does the order of piping matter?
Yes, the order of piping does matter. So it goes left to right. All right. So yeah, let me actually go into. These are examples of piping. Here are examples of using it. So the order of piping doesn't actually matter for invoking the processes. So just like if I type cat and it's waiting for standard in or waiting for some hardware or some file, that program, the kernel will wait for input. If you say read, remember we talked about read and write. If you say read on a file, the read, it's called blocking. The read syscall will block. It'll stop waiting for input until it sees the end of the file or until it sees the number of bytes that you've asked it to read. So when you wait on standard in, it'll just wait for that input. So if I have, say, cat passing to grep hello, both cat and grep are now running. So I can actually show you that they're running here with the process command. So you can see cat and grep, they're both currently running, but they're just blocked waiting for my input to standard in. So once I start typing some lines of code or lines of text, then you can see grep working. So yeah, these pipes go from left to right, and the left process, its output goes into the pipe, and the right process gets its input from the pipe, and so on. So then the input from grep comes from find, and then the output of grep goes to head, the input of head goes to grep, comes from grep, and so on. Does that make sense? So the order of invoking the process actually, I think, doesn't matter, but the pipes are set up to map standard out to standard in, left to right. Let me show this in a diagram. So what happens is bash, I'll actually show the bash, so this is the bash process. It will invoke the find process, and it'll invoke a process for grep. And by default, bash is writing to, so I'll just put the terminal here. Bash's IO is reading and writing to the terminal, and when it creates the find process, find will also be reading and writing from terminal. So what it does is it takes, so if this is my, let me color code the IO. I think that'll be a little easier to see. So arrow out is output, arrow in is input. So when the process is originally created, it inherits the parent process's IO. But what the pipe will do, what bash will do with the pipe, is it'll take this output and it'll redirect it to grep's input. So grep's input is originally from the terminal, but these inputs and outputs, the find output, will be redirected to grep's input. So let me show this again. So this is the output. This is the input to grep. And so what actually happens under the hood is this special new set of files is created called a pipe. And bash will redirect the output of the left program in the pipe. It'll redirect it to this special buffer, and it'll take the input of grep and redirect that from the pipe. So that way, whenever find is producing output, it's being saved here in the pipe, and grep, when it's reading from standard in, is reading from that pipe buffer. Questions on that? Does that kind of make sense? So if I've got yet another program here, like sort, bash creates yet another process to run the sort program, and it starts out reading and writing from the terminal, which is going to look a little ugly now because I have to go all the way over here. So that's where its output is going, and its input is coming from the terminal. And so what bash does is it creates a new pipe, takes the output of grep here, and redirects it to the pipe, takes the input of sort, and directs it from the pipe. Questions on that? Yeah.
Could you give grep multiple arguments, or would you have to run it multiple times?
Do you mean to match multiple things? There's an extension to grep called egrep, which will. So has anyone ever used regular expressions? Who's learned about regular expressions? Ooh, not many. Has anyone taken discrete? Do they teach this in discrete? Regular expressions? No. What's that? Discrete, okay, discrete 2. All right, so you have to wait for discrete 2 or just look it up. Regular expressions are a really common tool for doing string pattern matching. And there are, you can write patterns that will match multiple alternatives in the input. So I could say, actually, let's see, this, whoops. Whoa. All right, there's my header files. confusingly, the symbol for alternation is also slash or pipe, the pipe symbol. So there is syntax for checking for multiples. So I can have C files and .header files. Anyway, look at the grep command. Look up tutorials for it for regular expressions if you haven't seen them. They're super useful in programming. You'll encounter this quite a bit. Like pretty much every language has in their library has a regular expression processor. But don't worry too much about the syntax of it. It's pretty rough to look at if you haven't seen it before. But yes, you can make arbitrary patterns, arbitrary regular language patterns with grep. All right, other questions on piping? Yeah.
Show that command again.
This one? Yeah. All right, so we'll walk through it. So we've got 4 parts to this, 4 processes that are running. And remember, this is redirecting the output of the left process to the input of the right process. So we've got find, which just lists all directories and subdirectories. By default, it'll list all subdirectories and directories to the output. The input will take the egrep will take its input and only write those lines to the output that match a pattern. So it'll filter out lines from the input. Only lines that match this pattern. Don't worry about this pattern too much. It's just stuff that ends with .h, ends with .c. Okay, and then we've got some output from find. It's going to be a lot of files because there's a lot of header files here. This command takes whatever you give it to standard input, and it only prints the first 40 lines. That's what -n. By default, it does 20, so if you just did head, it would give you head is like the top of the file. There's another command tail, which gives you the bottom. And then sort takes whatever you give it in the input and sorts it in like alphanumeric or ASCII sort, and then writes that to the standard out. Because you're composing multiple functions together. Yeah, kind of in a sense, yeah. I don't know if there's a way to do recursion. And then, I can combine this with redirection if you want to make this even more complicated. So I can save the output of this using redirection. So the end of this pipe, remember, its output is going to whatever bash had. This was not redirected, so sort's output was still going to the terminal. But I can redirect that as well to a file if I want. So now the output of this, so you can see nothing goes to the output because standard output was redirected. And you can see now this output file contains the output. To make this even more confusing, I could also redirect standard error if I want from find. So one common thing I do is to redirect to null. That's an output that will just throw away the output. If you don't want to have messy log files. But I could save any errors I have to find error. So same thing happens with the output, but now my find error will have any errors. I didn't have any errors, so I would if I started from root. I'd have lots of errors. So I've got errors there now. Anyway, so this is a very large, complicated bash. But if you understand pipe and redirection, you can make arbitrarily large, well, there's some limit, I think, in the system to how many processes you can have, but you can make pretty much arbitrarily complex new programs without actually writing a single line of C code. You can just combine together these tools, and there's a whole bunch of, let's see, is there a manual page for this? So there's a whole bunch of Unix standard or POSIX standard tools called core utils. So there's another tool in here called Info, which is another documentation service. But there's a huge number. I mean, this just lists all of the standard tools you have available to you on pretty much any Unix system, besides maybe like embedded systems, which may have a different set. But this is, you have a huge number of common tools. And really, this is kind of you learn through muscle memory and experience, or just like, Googling. So if you're just aware that these kinds of tools exist, you can just like Google or go on Stack Overflow or whatever and say like, okay, how can I do this task? And someone has probably written a bash command to do this for you, or at least one that you can tweak. Yeah?
Like whenever you're running that, for each program, like
capacity for that program specifically.
Uh-huh. That's right. Yeah, right. So it's each, it's exactly the same as running a single process. I mean, actually, to really belabor this, this is the same thing as saying find and then saving it to out. Let's do user. Although one problem is that head here makes this a little less onerous. Let me do a smaller directory so this will actually end. Oops. So I've run find and saved it to an output file, and then I run egrep here, and I redirect its input from find.out and redirect its output to grep.out. You see how that works?
Yeah.
So redirecting it, yeah.
But as far as each program is concerned, it's like, running by itself, and it doesn't see anything else.
That's right, yeah. It's, because remember, they're processes. The process abstraction is that processes believe that they're the only running program. They have their own isolated memory space. They have their own independent access to the CPU, and they can't, without any additional facilities, communicate with other processes. But they can write to output, and programs can read from input. So this pipe is a kind of basic version of communication between processes. So you use the input and output, not just for file storage. Files are also used for communication between processes. So that kind of a good question. I mean, this is if systems classes will talk about this more in depth, but because processes are isolated from each other, if you want to do something like this, you want to do anything more sophisticated like having a network server, well, you need some way to read from other processes, so you can build up systems of multiple programs running. And this pipe is like a kind of early primitive version of inter-process communication. I don't even want to say primitive. It's just a kind of one tool for inter-process communication that you can use to communicate with them. So that I/O, that read and write, are also ways to communicate between processes. So it's not just about storing files. It's also just literally communicating to and from a process. If that makes sense. And this is actually the basis for network programming as well, because with network programming, you can think of the socket, the communication hardware, as just another file that you can read and write from. So when I run SSH, for instance, I can call SSH on Eustace, and I could echo hello world here on my local machine. So here I'm on my local work laptop, and I can pipe this to a Eustace program using SSH. So SSH is not just about logging in, it's really just running the bash program. So I could run the grep here on Eustace. So this is saying connect to Eustace and run the grep program on Eustace. And so this pipe, through the magic of network sockets in SSH, is doing network communication. It's passing this data through the pipe to the SSH program, which is then opening a socket and running this on Eustace. To kind of prove that this is on Eustace, I could pipe it to the host name program. The host name program prints out the name, the server name. So you can see that this is indeed running on Eustace and not my local machine. Yeah.
When you use the pipe oscillator, are both programs running at the same time?
Yes. Yeah. So you could imagine running them one at a time. And semantically that would work. It would be the same thing. It would mean the same thing. But what's done for kind of parallelism, to take advantage of the parallelism, is that they're all invoked at the same time. Yeah, and you'll actually write a shell to do this. And they're all just waiting for input. So again, this is kind of an OS topic, but when you have input and output in your program and you're saying, read from input, that read command, the meaning of the read command is to wait until you see input and keep reading as much input as you asked for. But this is actually a perfect opportunity for the kernel to switch processes. So when one program is waiting, one process is waiting for input, the kernel knows it's waiting for input because you called the kernel to ask it to give it input. So the kernel can keep track of which programs are waiting for input or running, and it can use that as information to schedule other processes. So they're all waiting for input at the beginning, and while that's happening, one process can be executing stuff while the other's waiting, or one process can be writing stuff out while the other one is waiting for input. And once some input happens, they can run in parallel, where one is processing the input while one is producing the output. So that's what happens in practice. The meaning of it is that each one runs one by one, but in practice, what the kernel does is it runs them all in parallel. And I can actually prove this to you, I think, by using a command that waits for input. So cat is reading from the terminal. I'm doing the filtering, et cetera, here. And so this program, it's not finishing; it's waiting for it to input. I'm going to show this in a little bit how to do, background processes. But you can see right now that if I type PS, which is the command to view all my current processes in my bash session, you can see that each one of these processes, each of these 4 processes, is already running. They're all running. They're just blocked, waiting on their read syscall for input to come from standard in. And once some input comes into cat will produce it to out, and then that'll go into grep, and it's this cascade of inputs. And this is even sophisticated enough where if you have like millions of lines of input, because the kernel is scheduling these processes to kind of share time between them, you may have the first million lines go to grep, and then once those million lines are processed, grep will stop. The kernel will put head and then process those millions of lines, and then cat will be returned to produce more lines, and so on. So the kernel has the freedom to schedule these in a way that the writer of the kernel thinks will be optimal for either the impression of concurrency or the speed of output or throughput. So scheduling is like a big topic in the kernel world. There's lots of ways to do scheduling for different applications. Take like an OS class or like a database class to learn about that. All right, other questions on this piping? Yeah.
Could you fork the output of one process into multiple other processes?
So you can fork many processes. You mean like have kind of a bubble here? Is that what you mean? Or you have like multiple processes and then they're all writing? Is that what you mean? With pipe, not strictly with pipe. So pipe is just one to one. But you could, there's a built-in command called while. So you could have a loop here that creates multiple processes. Now, only the first process is going to read the input from the pipe, but all of the output will go to the write pipe, if that makes sense. So basically, yeah, you could fork many processes. You could have a tool that forks many processes here, and you'd have to write a tool to duplicate that input if you wanted each of them to have the same input. You'd have to write a C tool to do that. I don't know. This would be something like a multiplexer. I don't know if there's a core utility for this, but you could write a core utility that multiplexes the input to lots of processes and then collect that output with a single process. Yeah, you could totally do that. I don't know if there's a tool in the core utils to do that for you, but you could write a simple C tool to do that. I don't know, does that answer your question? Yeah, you could do that. I mean, you could make, because you can fork as many processes as you want, and you as the programmer writing the code to fork those processes could arbitrarily, allocate input as you see fit. But you'd need some sort of multiplexer to do that. I wonder if there's a core utility for multiplexer. Multiplex input. Multi-call invocation. Okay. So I don't know if there is one. There is a, you can do this with that's a little different. That's 2 outputs. There is a tool to kind of multiplex the output both to standard out and to a file. That's useful in a pipeline when you want to save part of intermediate output. Like I do want to save the head output, but anyway, this is we're getting getting a little off topic, but yes, you'd have to write a program to do that. But the pipeline is meant for like a linear flow. Although you could use a while to invoke multiple processes in that pipeline. Hope that answers your question. Other questions on this? Pipelines? Oh yeah.
So if you leave an empty pipe, like at the end of sort, the default is always to give the output to the terminal again?
It's to whatever the invoking process was. So in this case, bash, currently its I/O is from the terminal and to the terminal. So yeah, the ends of the pipe, the first pipe has whatever the parent process had, which is terminal in this case, and the last element of the pipe has the parent's output, which is the terminal. So yeah, and when you're writing from bash, the last end of the pipe will be standard out. That's why, but you can close the end of this pipe to a file, like so. And similarly with the input, you could close the input of the pipe from a file. For instance, something like this. I broke my pipe somewhere. Okay, my pipe is broken. I don't know what I did. Oh yeah, find error. I broke something. Oh, I have a while here, that's why. All right, other questions on pipelines, pipes? Yeah.
Whenever you get the PS command, does the PID number correlate when the process is called?
It doesn't have to, but in practice, the kernel will just allocate them incrementally. So you can see that cat grep had sort. Oh, I still have other programs. I still have some processes running. So you can see that they are sequential, and that's just because when you call fork, the kernel will just allocate the next process ID. I don't know if that's required by Unix systems, but that's just how they're implemented. And I've got some old processes running here. All right, other questions on pipelines? So super useful tool. Take a look at the examples in the lecture notes if you want to actually try some of these out. And for homework, I've asked you to write one. So you'll write like a simple pipeline. This is a cool tool. So xargs. Xargs will convert standard in to arguments. So echo takes arguments and converts them to standard out. Xargs takes standard in and converts it to arguments. So let me show you where this might be useful. So let's say I want to list all the files in a directory. So here's find. And I want to run some program on each of those files. So I want to run, say, the file command to figure out what type of file they are. So this file tells me it's a directory. So if I were just to pass this to the file command, well, that doesn't make any sense because file takes the name as an argument. If I use xargs, this takes each line of this input and turns it into an argument to file. So now when I run this, it will run file on every. It's like saying while each line of the input run file on it, but you have a command line tool for doing that. So xargs will take each line here and make it an argument to the program that I have. Also kind of a useful tool. I use this frequently in scripting. Anyway, so here's some examples. Here's some long examples. This is me doing a little kind of metrics of source code for my research. This is a useful trick that sysadmin and ARC showed me. You can pipe both standard out and standard error at the same time if you want to search both, the standard error and standard error. Useful trick. All right. Questions on pipelines? Any more questions on pipelines? Yeah.
Is there a way to change kind of, how at the end of the pipe it goes back to the bash, the output? Is there a way to change that default?
Yeah, so that's what the redirect will do. So I can redirect this output to a file. So I can use redirect to change it to a file. Is that what you mean?
All the time.
Oh, I don't think so. I mean, if you did that, then bash, you wouldn't see the bash. You could like when you invoke bash, you could redirect its output, but then you wouldn't be able to see what you're typing. But yeah, you could you would have to do it when you invoke bash. So for instance, I could, well, let's see. I don't know if this will work. Let's see if I can invoke bash. So you can always invoke bash again and just get a new shell. And you can see bash is running twice. So if I exit, I'm back into the previous bash. So let's see if I can actually. Yeah, it doesn't seem to let me do that. Oh, wait. Oh, I think it just ran and terminated. So I think it's not waiting. So if I, no, it is running. Oh yeah, I can't see the output. Yeah, right. So this actually worked. So you can see there's the output of the program I ran. So yeah, you can invoke bash like this, and then when I do my pipe, it's not going to go to the output. It's going to go to bash.out. So you should see in bash.out the output. But that might be very confusing if you're doing this interactively. All right, other questions on piping? All right, before I get to this, let me do attendance, which I forgot to do earlier. Okay. So let's finish up process management in Bash. So this will give you some more tools for working with processes before we actually go into doing like systems programming. You probably know this. Control-C will attempt to tell a running program to terminate. So if I'm running find, for instance, and it's just running for a very long time, Control-C will ask find to terminate. Now I say it asks find to terminate because find does not have to terminate. If you really wanted to terminate, then so here find is still running. To force it to terminate or basically give it an unmaskable or unignorable signal to die, you can use kill -9, which is going to tell the kernel to kill. Oh, it already exited. That was fast. So all right. It's already exiting, but this will force it to die. All right. So Control-C. All right. So you probably saw me using this already. Control-Z will pause a program for you. It'll tell the kernel to no longer run this program. It'll kind of freeze it indefinitely, and you can see what programs have been frozen or put in the background using this jobs call. So what Control-Z does is it's just something with Bash. Bash, your I/O will be inherited by the child. Control-Z will put that running process into the background for you. And so to resume it running in the background, use BG for background. And if you want to bring it back to your terminal again, so you can interact with it, use FG for foreground. So FG for foreground. So foreground means the process is running on the shell, so you can interact with it. And background means it's running as a separate program from the shell. So remember last time we saw that there's lots of running programs on the machine, lots from other people. But if you want to make a new process and you continue to use your bash shell, you can use this foreground and background. You can also do this directly from the command. If you put an ampersand at the end of your command, it will run it in the background. So this is ampersand at the end of the command means just run it in the background. So you can see here it's immediately already running in the background. Okay, so some more information about background processes. I just showed this. You can immediately put something in the background with this ampersand sign and foreground FG in background to move it to a background process versus a foreground process. So for instance, if I have cat and I put it in the background, it's not going to take any of my input. So I'm back in Bash, but if I foreground it again, I'm back in cat and it'll start taking my input again. So yeah, you can view running programs with jobs, the jobs command, and you can pass one of the index of a job for foreground and background to target one of these to foreground for you. Anyway, something you may use if you're doing like a lot of like sysadmin or doing some more like hardcore Bash stuff. All right, but what I really want to show you with this is a very, what I call quick and dirty development workflow on Eustace. So I'm guessing for many of you, what you're doing right now is you're opening up your program, maybe it's your FS program, and you're probably really frustrated with me that I'm making you use a command line editor, or you're just using VS Code or something, which you're going to blow up your disk quota maybe if you do that. And you're in the middle of programming down here somewhere down in this file, and then what do you have to do? You have to save and quit, right? And then you open the file again, and you're back at the top. Kind of annoying. But you don't have to do this. Instead, you can leave Emacs running. So this is the beauty of the process management. You can leave Emacs running with Control-Z. So Control-Z will pause the process, put it in the background, and now I can continue on with my compilation and testing. Oops. Oh. I can continue on with my compilation and testing. And then FG, what does FG do? Foregrounds the process, yeah. So if I hit FG, Emacs will resume exactly where I left off. And so I don't have to quit Emacs. Be careful that you don't invoke multiple versions of Emacs because they'll all sort of contend for writing your file if you have unsaved stuff. Make sure you save before you do this. So instead of like save and quit, Control-X, Control-S, and then Control-X, Control-C to quit, do Control-S, Control-S to be save, and then Control-Z will pause it. And you can do your stuff on the command line. And then FG to resume, yeah.
So if you pause without saving, it just erases all the new content you have?
No, it's still there. So it's in memory. The unsaved content is here in memory. So you can see these double stars here at Emacs mean you have an unsaved buffer. Unsaved stuff. It's still going to stay there. Now, Emacs does have an auto save feature. I think this is the autosave file. So it'll try to preserve any, like if I kill this process right now, if you like hang out, you log out or you kill this process, it seems like I lost my file, but I think it did not have time to autosave. It's the hash file. Oh no, it's not the hash file. So if you give it some time, it will autosave, but it's not that fast. It does autosave periodically, but I recommend just saving after you make any changes. Just save. So Emacs does have an autosave feature, but it takes some time to invoke, I think. So just actually here it is. So it's locked by another process. So so it thought that another process had this file open. But anyway, save your work after any change you make. Save your work before you pause. Pause it, and then do your stuff on the command line and FG to resume. And so this will make the workflow on the command line much faster for you because you don't have to keep moving around the file. Yeah.
So if you have your file and then you make a change and then you pause, let's say folks that install this version.
Yeah. If you don't save it, the file on disk will not be updated with your changes. So I can show this here with this is my unsaved content. So here I didn't save it. You see the double stars here. And if I print out hello.c, you can see that content's not there. So this is like in memory in the Emacs process. Then when I save it and pause, you can see the file, this content is there. So just by you should be saving anyway. Just always save. I save kind of as muscle memory whenever I make any changes. I just save as muscle memory. when I'm coding. You can't see me save it, but you can see that those asterisks on the bottom, they go away when I save. So use that workflow. That'll make things, I think, a lot easier on the command line. You don't have to keep reopening the file and moving back to the line you were at. You can just use Control-Z to pause and FG to resume. Now, be careful that you don't open many Emacs instances. If you do that, you can tell here by running the jobs command. So if I run the jobs command here, you'll see that I have many Emacs open. So just use FG to open all of them and make sure you don't have any unsaved stuff, because you might overwrite. You might overwrite stuff. Yeah.
So I'm assuming we run the program and then log off it'll just close it.
That process will be closed. Yeah, that process will be closed. I'll show you just briefly at the end. There's a tool you can use. Eustace does not permit it, but if you have your own server, there's a tool you can use to actually save your bash session called a terminal multiplexer. I have that as an optional section. I'll briefly go over it, and you can look. I use this tool all the time on servers so I can keep my sessions open and my Emacs editor open. Yeah.
When you run jobs, what do the plus minuses mean?
I think they mean, that's a good question. They might, I don't know. Let's see. I think they might mean which one was the most recent. So FG has a default. Actually, don't know. This is my guess. When you type foreground, there's a default job that it'll bring back up. I think it's the last one you ran.
So if we create a new Emacs, then we should be able to see some plus minuses.
Let's see. So it said plus. Yeah, I don't know. I don't know what minus means. I don't know. Yeah, I don't know. I have to Google it. It may be the last one that you backgrounded, and so when you type FG, that's the one that's gonna. It might be that. Yeah, I don't really know. Yeah, it might be recording the order in which you put them in the background, but I actually don't know. Good question. Ask on NetStem, and I'll look it up. I'll try to figure it out. All right. So in the last minute here, I have an optional section here. So do you have a question? Yeah. Jobs is built into Bash, because Bash is the one that's doing this process management. So the notion of a background process is specific to the shell. To the kernel, they're all just processes. It doesn't care. It doesn't know to have the difference between a background and foreground. Foreground just means your terminal is the I/O is connected to that process. All right, so terminal multiplexing, this is a tool. I use Biobu. You can use Screen or Tmux. There's a bunch of these tools. And I'll just show it really briefly. So you can, it's kind of it's like a remote. You ever use remote desktop on Windows? It's like remote desktop, but remote terminal on a machine. I can, it's also like a windowing system. So I can have multiple bash sessions at the same time. So here's bash 1, and I can switch between them. So I can have multiple bash sessions, and I can also exit from it and save it. And then when I log back into the server, I can restore this session and have all my currently running sessions open. Now, Eustace will kill all of your child processes when you exit. So I found this out the hard way when I didn't check that, and I demoed this last year and was like, oh, it's not saving my Biobu. But it has a setting to kill your processes. If you have your own server, you can do this where you actually exit the server, you exit out of Bash, and then your Biobu session and all those Bash sessions will still be running just where you left off. I use this all the time in my research work on servers. Actually, well, I don't have to any time, but I could let me know next time. I can show you on my server this stuff actually working, where it's retaining the session in the background. But all right, so that's terminal multiplexing. Let me know, come up if you have any questions. That's the end. We're at 10:20, so the end of class. And homework is up. It's just homework from today. And have a good one. See you next time.